This is fundamental problem 13 from chapter 17. The uniform 60 kilogram slender bar is initially at rest on a smooth horizontal plane when the forces are applied. Determine the acceleration of the bar's mass center and the angular acceleration of the bar at this instant. Because the surface is smooth, we don't have a force of friction. It's a horizontal plane, so the force of gravity is pointing into the page. That's balanced by the normal force, which is pointed out of the page. It's a slender bar, and so we can use that to look up the moment of inertia in the back of the book. And for this section, we can use Newton's second law and then sum up the moments about some point and set that equal to the moment of inertia about the same point times the angular acceleration. I'm going to start off doing Newton's second law, and that will tell me what the acceleration of the bar's mass center is. So I'm going to say the x direction is this way and the y direction is this way. The forces are given to me here. There's a 20 Newton force downward, well, in the negative y direction, and an 80 Newton force in the positive y direction. So 80 newtons minus 20 newtons, this is the sum of the forces in the y direction, is 80 minus 20, that's 60 newtons, that's equal to the mass times the y component of the acceleration of the mass center. The mass of the bar is 60 kilograms. So 60 newtons divided by 60 kilograms gives you 1 meter per second squared. So that is the y component of the acceleration. For the x component of the acceleration, you have your two forces here. This is the x direction. For the sum of the forces in the x direction, you have 0. So that's the mass times the x component of the acceleration. So the x component of the acceleration is 0. So you can say the acceleration of the mass center is equal to 1 meter per second. And you can either say upward or you can say that is in the j hat direction. Okay, so we found the acceleration. Next, we need to find the angular acceleration. So I can either use equation 17-19 for the instantaneous center, or I can use the sum of the moments about the mass center is equal to the moment of inertia about the mass center times the angular acceleration. I'm going to go with this equation here and sum up the moments about the mass center. That's equal to the moment of inertia about the mass center times the angular acceleration. This is a slender rod. Can turn to the back of the book. And for the slender rod, for an axis going through the mass center, the moment of inertia is 1/12 times the mass times the length of the rod squared. So this is equal to 1/12. The mass is 60 kilograms. The length, that is 0.75 plus 1.75 plus 0.5, that's 3 meters. So that's times 3 squared times the angular acceleration. And 1/12 of 60 times 3 squared is 45. So this is 45 times the angular acceleration. Then I have to do the sum of the moments here. So if I look at the diagram that they give me, well, first of all, I'm summing up the moments about the mass center. The total length of the rod is 3, so the mass center is at a distance of half of 3, that's 1.5 meters from this end of the rod, and also at a distance of 1.5 meters from the other end of the rod. This distance here is 0.5, so if this is 1.5 and from here to here is 0.5, then this distance is 1 meter. And if this is 1.5 and this is 0.75, then the distance from here to here is 0.75. Now that I have those distances, I have my forces, I can find the sum of the moments. The 20 Newton forces would cause rotation in the positive direction, and the 80 Newton force would also cause rotation in the positive direction. So those add together, and it's 0.75 times 20. Plus 1 times 80 for the sum of the moments, and that is equal to 45 times the angular acceleration. And so for the angular acceleration, I will let you finish the calculation on your own. You get 2.111 radians per second squared. And that concludes fundamental problem 13.